So last time we learned stochastic gradient descent. So let's review it a bit. This is basically stochastic gradient descent. But let me quickly recap what stochastic gradient descent is about and what's the difference between gradient descent. So, okay. It's recording. Okay, so. So difference between gradient descent and stochastic gradient descent. And first, of course, for the stochastic gradient descent, let's first review what is our loss function. So our loss function is in general written in this form. And our loss function is the average of the element-wise loss. For example, this loss function may be written as this. Okay. And we redefine this one as f sub I of W. And for example, this can be something like a least square problem. For example, we choose a mean square loss. We just do, this is the norm of our neural network. Okay. So this is our neural network's output with W as our neural network and with the ith sample as our input. And we want this one as close as possible as our true target. And then we take square. Okay. So for example, this is the element-wise loss. And of course, for classification problem, of course, we can have cross entropy function. The other example is we have this so minus yi times the natural log of this guy minus 1 minus yi natural log of natural log of 1 minus h of xi w. And of course, when we talk about classification problem, we kind of abuse this notation a bit. This means we already applied the sigmoid function. We applied the sigmoid function on our output here. Okay. So this is element-wise loss. And so in general, SGD, okay. So the GD computes the gradient for all samples. Okay, so okay, so the GD computes the gradient for all Fi from 1. So from 1 to capital N. From 1 to capital N. So we have capital N that many samples, and at each iteration, okay, The difference of SGD is at iteration, we just compute one sample. So at each iteration, compute the gradient only for a randomly chosen sample, ik from 1 to capital N. Okay. And what is the advantage? Like intuitive advantage of this is, for example, in the MNIST problem, when we wanna design a neural network to recognize all the 10 digits, if we examine the data carefully, we will find that there are many samples. They are like looking alike. For example, in that sense, when our model sees one sample, it kind of remembers that sample, and the next time, like when it sees a similar sample, it can recognize it. So we don't have to let the model see so many repetitive samples. We only have to let the model to see some representative samples, and it already learned like the representation of how the 10 digits are constructed. So the idea behind SGD is, we'll see later in the proof, is our samples are drawn from the same distribution, so they kind of similar. Okay, we can expect, we train a model perform very well on one data set, and then we change to another. For example, we train our model to be able to tell the difference between cats and dog, but then we let the model see, okay, so can you predict whether this is a plane? Of course, the model cannot. So, and we'll see later in the mathematical proof why this is the case. And so by the way, I want to emphasize that normally this is without replacement. So usually the choice, so usually this choice is without replacement. Okay. So it means if we have used one sample in SGD, we put it into the used basket. All right. So we don't choose it anymore. And in our current, so we'll introduce a new term. It's called epoch. Okay. Okay. So one epoch for SGD is the model. So if the model has been applied SGD for all, like sample 1, sample 2 up to n, we call this training procedure a epoch. So we say the train has done one epoch. Okay. So as we can see here, if we use this definition, one iteration for gradient descent is actually has the same, like almost like at least the same magnitude. So same complexity with one epoch of SGD. All right. So one iteration of gradient descent computationally, the complexity, even though we have to take into account of overheads and etc., but complexity-wise, it's equivalent of one epoch of SGD. And in our next coding assignment, we're gonna observe that one epoch of SGD performs much better than one iteration of gradient descent, even though their computational complexity is the same. So now let's look at the proof. Okay, so proof of convergence. So by the proof of convergence, in our case, we still assume our loss function is Lipschitz continuous and strong convex. Okay, so this is strong convexity, and this is gradient f is L Lipschitz continuous. Right. So we assume we have that, and normally we further assume, and the L, so L is like much bigger than our strong convexity constant. So now let's look at the proof, and this IK right here, so let's recall the definition of F sub I. F sub I is the element-wise loss function for the ith sample. So if we have, so let me scroll up, yeah, right here. So F sub I of W is like element-wise loss function, for the ith sample. If we have a sub IK here, it means we just randomly, so this IK is a randomly chosen sample. So from 1 to I. Okay. And now we perform the same error equation type of approach with gradient descent, but here's a caveat: is so instead of like we have some spoiler last time, instead of like proving a pointwise convergence, by pointwise we mean without this randomness, we have to consider like an expectation. But first, let's write down the error equation. Okay, so the error equation. So the error equation we can have is WK plus 1 subtract W star. W star is like our best possible parameters that minimizes our loss function. It means it's, for example, whether we can find the best neural network to achieve the minimum. So the answer is we will not discuss whether this thing exists and whether this thing is unique. The answer is the uniqueness is quite straightforward. It's not unique, okay, because we can have permutations and etc. But we don't discuss it right now. So we just assume, okay, there is a W star that is a local minimizer. So this equals WK, W star, and subtract alpha gradient of Fi, WK. And of course, we can insert So this is one of our old tricks that we can insert gradient of f w star. So this is this w star, and this equals 0. And I want to emphasize that this is f, this is fi. So how to bridge this difference is so this is a common trick used in optimization, is we insert, some term that can be that can serve as a bridge. So the answer is we just insert this term. So we insert the gradient evaluated at the current iterations parameter, neural networks parameter, and we subtract alpha. So as we can see here, we minus this guy, which means we have to plus it at somewhere, which is, so it's gonna be, so this is plus, sorry. So this is plus, and which means we have to minus it. So, and the minus, okay. If we look at these two terms, the blue terms, actually, they are the same term that, I think this is ik, sorry. This is ik, I sub k, my bad. Okay. This is a random term. There is randomness in this term, okay? So let me say, the randomness comes from here, okay? There is randomness in this term because we randomly choose a sample, but there is no randomness in these two terms, and we can proceed as last time. So if we remember, so last time what we did was, when we combine these two terms, what we can get is I minus alpha Hessian of f evaluated at, so I'm gonna use theta of k. So this is a point between wk and w star, all right? So this is using Taylor expansion and multiply with wk minus w star. But then we have to minus this, okay? So if we think about this, now we think about this. If we only have this term, it's a gradient descent, all right? It's a gradient descent and it's convergent if we assume, because we have here, all right? So we have Lipschitz continuity and strong convexity, and when we use Cauchy-Schwarz inequality on this, we can show that when alpha is chosen sufficiently small, and this will be a contraction. Okay, now the key term is here. Now why I'm saying we have to assume the data, they satisfy the same distribution, or say there are similarities between data, it's here. We think about this. This is one sample, all right? This is one sample, and this is a mean, okay? So now let me add the remark here. So this is gradient for one sample, but this is a gradient, the gradient average for all samples. Okay. So the intuition comes here. When we have something, let's say our data is well distributed, and that's when the SGD will work. If our data is like a garbage, then SGD won't work. And actually, if let's say if our data is garbage, then the gradient descent even won't work, because this function will be bad. Okay, so there is a computer. I mean, I learned in my undergrad computer science class. So there's a proverb in computer science. It's called garbage in, garbage out. So actually, it applies perfectly to data science. So actually, for all data science, even though we have so many complicated neural network, but the biggest thing is the data. Unfortunately, we won't learn many techniques about data in our class, because this is an optimization class. But even though I don't teach any data related class, but this is an optimization class, like I said, but still the most important thing in data science is data. Okay, so how do we handle the data, etc. So how do we unearth the irregularities in data, etc. But the intuition is this should be close to the average. Okay, now let's use the error equation. So now let's use the error equation. Let's bound the error equation, but we use the expectations. So the expectations of, let me still use W. Okay. So, and we plug in this in our error equation. All right. So in our error equation, we have two terms, right? So we have two terms. So now let's recall the norm. So we will have basically the norm of I minus alpha, the Hessian of f theta k, wk minus w star. So this is our first term, and then our second term is gradient of fik, evaluated at wk. Let me make this thing smaller, resize. Okay. Then subtract f of wk, parentheses, norm, and then bracket. Okay. Square. So this is how we use error equation. Is we square, we take the norm, and then we take the expectation. So this is called second moment, and it's a common like analysis method in probability. But let's just say we adopt this methodology, and then we have this is the norm square of two vectors or two tensors. So here we apply. So here we apply our Euro. So let me put the formula here. So for example, if we have a matrix A, we have a not necessarily matrix, just vectors. So A plus B square, and this is nothing but A square plus B square plus 2A inner product with B. So this is our this is our Euro quadratic formula, but in the world of tensors and vectors. So now let's apply this thing to this formula. And moreover, so taking expectation is like taking integral. It's a linear operation, so we can separate the expectation of three terms. So for example, so the first one is I subtract yeah, let's not use Cauchy-Schwarz first. Let me just keep it as it was. So this is the first term, and then we have the last term, that is and alpha is like a fixed number. So alpha is a fixed number. It has nothing to do with the stochasticity, and we can safely pull that out. So sorry, this is plus. So it's going to be alpha square, okay? And expectation of gradient of Fik. So this is where the stochasticness come from. Okay. And lastly, we have a so we have this term that is the cross term, that is minus 2 times alpha expectation of gradient of Ik, Wk, and gradient of Wk, Fwk, dot product of yeah, let me move this a little bit to the left. Okay. And then we have a big bracket. Okay. Yeah, let me use color, different color to denote the bracket. So let me, for example, let me use this bracket to denote it here. And let me use a more brighter color. Let me use this color to denote this bracket. Okay. So essentially, we apply the quadratic formula. It's nothing fancy. We apply the quadratic formula here. We have this term. We have this term. This term is actually, there is no randomness in this term. The only randomness is this term. So the expectation of this term is it without expectation. So I know some of us may be curious, isn't like the W stochastic? So it's not directly stochastic. So when we take the expectation, the integration is directly taken on the random variable, which is Ik. Okay, so the Ik is the only randomness in this equation so far. And now we have Ik, right? This is not random, so not random. Okay. So then the expectation is on this term. However, if we find the good thing about it is if we take expectation of this is like one sample. When we take expectation, it's like the sample mean, and it actually equals this. Okay, so the expectation of is 1 over n sum with all n, and the gradient of Fi. Okay, so it actually equals which means the third term, the cross term actually is 0. Okay, so this term becomes 0, so it's gone, and it's actually one of the key in the proof. So I'm not sure if we can finish this today, but let's hope we can finish it. So I may be a little bit rushy in this class, because we want to learn how to code this on Friday. But if we can finish it, we'll come back it on Monday. So that's which means so this will become 0 when we take expectation. So the third term becomes 0, and we are only left with the 2 terms. So okay. So, and let's say let's give this term a name. So this term is 1, and this term is 2. So what happens is the expectation of the difference in next iteration, okay, is equal to 1 plus 2. And moreover, for 1, okay, so for 1, we have learned that it's less than 1 minus, so I minus alpha, the Hessian of f theta k square. So everything is squared, and there is no random like in this term, but let's take the expectation here. Okay, and then plus 2, so 2 is right here. Okay, so plus 2, and instead of 2, we just write down is m. Okay, so where we assume the expectation of the sample gradient subtract the overall gradient, okay, is less than or equal to m for any ik and for any w. All right. So there is a double fold. It's like so this one is really like taking the second expectation then on w. Okay, so on average, like how w will change. So now, so this is our assumption, okay, and the interpretation of the assumption is the gradient of each sample. So again, this is a gradient. So on average, the gradient of ik's sample loss, and this is the gradient of the overall loss. Okay, we assume on average, when taking the second moment, they are less than a certain number, this capital M. All right. And now, what's happened is we take, okay, so we take so we let k goes to infinity on both sides. Okay. Both sides, sorry. And we assume, so assuming WK converges to W infinity. And this W infinity might not be W star. Okay, so but we just assume it converges to like a fixed point. All right, and this fixed point might not be, so this may not be W star, which is our like best possible neural network. But if we train using samples, and we may show that it's sufficiently close. So, and moreover, for this one, okay, when we have this assumption, so when we have this assumption, which is L much greater than this mu, and moreover, we have also this assumption, that is a strong convexity and Lipschitz continuity on every point. So I skip the proof about it here, and we learned in 449, so that this is less than the maximum of 1 minus absolute value of 1 minus alpha mu and 1 minus alpha L. Okay. When alpha is sufficiently small, these two will be positive. So when alpha is sufficiently small, both of them will be positive, but this guy is bigger than that. So we have square. So which means this is this equals 1 minus alpha mu square when mu is much less than L. Okay. So now we have our final result. That is, when we let the left side go to infinity, we have this is 1 minus alpha mu square, and this is the same limit here. So let's write down the limit. What we have here is E W infinity subtract W star square less than or equal to 1 minus alpha mu square E that. Okay. Plus alpha squared. And if we solve for it, you know, this is positive, right? And this is a number. We assume this is a number less than, for example, 1 minus alpha mu is a number less than 1. So we choose, choose alpha sufficiently small such that 1 minus alpha mu is less than 1, or alpha mu is less than 1. So 1 minus alpha mu is less than 1. But greater than 0. Okay, so but greater than 0. Or I should say absolute value, sorry. Yeah. And then if we solve for it, we're gonna get 1 minus alpha mu square of this is less than or equal to alpha square m. And now, so this is where the SGD likes limit. And this is our best possible neural network. So let me add a remark here. So this is the limit of our stochastic gradient descent. And this is our best possible neural network. So their difference, as we can see here, is less than. So we simplify this. This is going to be 2 alpha mu plus minus. So this one gonna cancel, and we're gonna have 2 alpha mu minus alpha square mu square. And if we divide this to the right, we have the convergence. Okay. And we can actually cancel one copy of alpha, so we'll get the convergence. So this is a convergence. Okay. And we try to interpret this result. So in our gradient, in our gradient descent, algorithm, if we scroll back, we're gonna get the gradient descent algorithm. There is no expectation. It's just like a vanilla contraction. Like there is no expectation. There is no on average. It's like when we choose the step size sufficiently small, it's gonna converge. It's gonna converge to like the best possible neural network. However, I don't think I have time to finish this, but so we have actually the observation. The observation is says the following: instead of a pointwise convergence, okay, so SGD with a sufficiently small step size or learning rate alpha, okay, it converges. And this is not even, if we learn real analysis, it's not even convergence in measure or convergence in probability. This is because if it's that, this is zero. Okay, so this is zero. So the expectation is zero. And this is, the convergence is even weaker than those. For example, if in real analysis we learn convergence in measure or convergence in probability, or like convergence in moment, it's even weaker than that. It's it converges to a region around, or say a neighborhood around the optimum, like the local minimizer W, okay, with a given variance. Okay, so this variance, what do we mean by variance is this essentially, this is the variance, okay, with a given variance. The variance depends on this M, and of course it depends on mu and L, but we only see mu here is because we assume L is much greater than mu, so it actually depends on this this M. So, and let's recap what is our M, and this is our M, okay. So it is on average like the square difference, or say the variance, or say the second moment of the sample's gradient of sample's loss versus gradient of overall loss, where essentially we assume every sample are not too different, from the overall distribution, so that this variance is bounded, okay. And moreover, so it's it's like it's natural to ask the following question. So we'll try to answer that on Monday. So question. So for example, if we look at the convergence, okay, if we look at the convergence, so it converges to a region around the minimum. Okay, so it's of order alpha, right? So we assume this m is like a fixed number. Then, and when we choose alpha is small enough, this term's influence is negligible. Essentially, we have like a big O of alpha, and it converges to 0 as alpha goes to 0, right? So a natural question to ask is the smaller the learning rate alpha is, the better the convergence. So that's a question we will try to answer next time. The answer is no, by the way. The answer is no. So the answer is there is a trade-off, but let me just write it here. So there is a trade-off. Okay, but the answer is generally we cannot have this dichotomous answer of a yes and no, but there's a trade-off. So it's called no free lunch theorem. And but so that's it for today. And next time, the next class we'll learn how do we code stochastic gradient descent. On Monday we'll come back. We'll try to answer this question: is a smaller learning rate better? So that's it for today.